Good afternoon, everyone. Brian. My name is Ashish Kumar Singh, and I will be speaking about my project Laser for Magnesium. This project is being carried out under the Marie Curie postdoctoral fellowships, and this is being carried out here with oh, uh, the project is being undertaken here with Dr. Ūbelis's lab, and we won this project last year. And um, the title of the project is Laser for Magnesium, the influence of laser wavelength feedstock quality on the optical properties of magnesium alloys. And this is specifically for industrial purposes wherever we need to do laser treatment of magnesium alloys. So I'll be quick. First and foremost, why this topic? So the purpose is to investigate or better understand the optical material properties of magnesium alloys, so that we can better understand how magnesium alloys specifically react to processing with lasers. So this particular topic is relevant to the demands of aerospace industry, which especially from ESA, who have a deep interest in the additive manufacturing of magnesium alloys. I will speak why, but to highlight the reason is that the conventional infrared lasers, which are industrially used for processing of metals, they have poor processability with magnesium alloys. Specifically because the reflection of laser light by magnesium alloys is very high, and the absorption is very low, due to which we have to figure out ways to develop or find a laser system that works best with magnesium alloys. Due to this problem, the laser-based additive manufacturing of magnesium alloy currently faces significant problems. However, we see that titanium alloys, steels, and even aluminum alloys are being successfully 3D printed with the lasers. The perceived benefits of this research would be that it would be directly applicable to the additive manufacturing of magnesium alloys, and it can be applied both to selective laser melting and laser directed energy deposition, which are different in that the feedstock is different for both these processes. For selective laser melting, it's a powder bed fusion process, and the laser directed energy deposition process uses a feedstock in wire form, but both of them use laser as the heat source. And if we can successfully do it, then it can also result in production of components and parts that are lightweight, specifically needed for the space sector. So a brief overview of magnesium alloys. It's the lightest structural material. It's 33% lighter than aluminum and 60% lighter than titanium, although its strength is slightly lower than aluminum. But given that it's significantly lighter, there is a particular interest in replacement of aluminum alloys with magnesium alloys, and specifically for space sector and defense. So these two sectors are highly seeking to produce parts like these from magnesium alloys. So in particular, this part is a thermal. It goes on a satellite, and they were able to achieve 20% weight reduction with this. With similar mechanical performance, and also for spacecraft arrays where these are used with the sensors and everything. So here as well, they were able to achieve up to 25% weight reduction with similar performance. Also, so these kind of parts are much easier to build with 3D printing than with conventional machining. So that adds to why the laser interaction of magnesium alloys should be studied more. So a brief overview of the specific process in question, selective laser melting. So here we have a laser source, which is uh, uh, focused by lenses, and it's scanned over a surface of a powder bed, and selectively sintering those powder bed using a laser creates the 3D part layer by layer. And how the metal or the metal powder reacts with the laser, we can see that it's a complicated thermal process where there is radiative uh, 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 emission of the laser beam. There is some absorption, and a lot of it is just scattered or reflected from the surface, and that reflection can be both diffuse or specular. Most of these systems, they use infrared lasers, which are 1050 nanometer about their range. And the processability and the energy efficiency of how much energy that we put into the system is being effectively used is a function of the laser absorbance. So if the metal doesn't absorb enough of the laser, then the efficiency goes down. And both of these properties are dependent on the laser wavelength. And the absorbance A here and the reflectance, they are related by this equation right there. So reflectivity values for some of the common metals is shown here. So here we can see this is the infrared wavelength, and the absorbability is about 20% for aluminum. Nickel is slightly higher. Steels have much higher than that. And there's a general trend that as the wavelength increases, the absorbability basically decreases, and that makes it very difficult for the entire system to be efficient. And such data or such study has not been performed for magnesium alloys, which are in the recent years, they are gaining a lot of ground by material scientists and designers. So one case in point is that similar work was done for copper, and they found out that the best laser for processing copper would be a green laser, so 535 nanometers, and that increases its absorbability by 50%. So here's a brief overview of the experimental and the theoretical research plan that was followed here. So these three are the most common industrially used magnesium alloys. So AZ31, AZ80, ZK60. So the AZ just means aluminum and zinc. So these are the additives into the magnesium, and ZK is zinc and zirconium. Especially the ZK60 is in demand by the space sector because of its higher strength, like very close to some space grade aluminum alloys. And so the reflectivity was measured for these alloys. I also turned these alloys into powder, which I will not talk too much here. And the dielectric properties were measured by Reels analysis. And finally, the processing of magnesium alloys with the laser that will we find to be the best one will be performed. And in the theoretical part, just to see whether our experiments are giving us what we want and how we can make modifications to the alloys that we are using, I performed DFT calculations to obtain reflectance of pure magnesium and its alloys, and also to obtain dielectric properties of magnesium alloys from the Reels analysis, which is the reflective electron loss spectroscopy. So for the spectroscopy, so this machine was used to measure the reflectivity. All the samples were polished to mirror-like finish, and the Agilent Carry 7000 spectrometer, this machine over here, this was used for wavelengths from 300 nanometers to 2000 nanometers. Here are some of the specifications of the testing and 5 measurements for each. And here you can see the 3 alloys and their composition. So the AZ series has aluminum and zinc, and the ZK series has zinc and zirconium as the primary alloying elements. So for the reflectivity results that I received was that the AZ series, both of these, the black one and the red one, they show similar trend, but there is a difference in their reflectivity, mainly due to the difference of the concentration of aluminum in them. And the ZK series had a very different behavior than the AZ series, and this was and this is something special, something peculiar, because most of it is magnesium anyways. So why this behavior here? So to understand this, the DFT calculations will be done. And here are some of the highlights of this, the result. So we can see that, so if we compare the reflectivity at the infrared laser wavelength to, let's say, 450 nanometers, but, which would be somewhere over here, there's a reduction of a significant reduction for the reflectivity for the AZ series. So this immediately tells us that if we use a different wavelength laser, let's say, so this wavelength lies somewhere in the blue spectrum. So if we use a blue laser to process magnesium alloys, so the reflective loss of the laser beam would be much less, and the processability of these powders would be better. One more thing, since these samples were highly polished, and most of the engineering materials that are used for manufacturing, they are not in that state. So surface roughness will also play a significant role in the reflectivity, which will be studied later on, to see how the surface roughness increases the diffuse reflectivity of these alloys. So here is a synopsis of the DFT calculations. So so this is a free-to-use package known as Quantum Espresso, and I made a 4x4x1 supercell of hexagonal pure magnesium to do these simulations. So here is the lattice that was used for the experiments. The number of atoms is 64. These two things are very are like parameters for running DFT simulations, and here there is an illustration of the high symmetry points for the Brillouin zone of hexagonal lattices. So around these points, the calculation are done. And so basically what this does, density functional theory does, is it calculates the structure of the bands and how the structure of the electrons and the atoms react to any incident changing electromagnetic waves. So here is preliminary results of the DFT results. I'm still in the process of doing this and perfecting this. So here is it. the so-called band structure of magnesium. It's very chaotic. It's difficult to understand, but so what it shows is that how much energy is needed by a phonon or an electron to pass through the matrix of the metal in question. But for my purposes, these two results are more important. So this is the dielectric function, and this is the refractive index and the absorption coefficient of pure magnesium that I was able to get from the DFT simulations. So this part has to be perfected more. I need to use a stronger computer to basically get more converged solutions. But when I get them, these results will be compared with some experimental results, which is obtained by Reals analysis. So this is a real spectra for pure magnesium that was performed on 95 electron volt energy. And this spectra will be processed through deconvolution methods to get energy loss function and ultimately the dielectric and optical properties. And these properties will then be compared with the one that I get from theoretical models, and that will so that should tell me how the alloying elements, be it aluminum or zinc or zirconium, how they affect the optical properties. So in conclusion, I would say that the reflectivity of magnesium alloys is pretty much constant for a very wide range, and it starts to drop around 500 nanometer, and it shows that the IR lasers can be replaced, and more better laser systems can be developed or straight away bought to do processing of magnesium alloys. And I have to use high performance clusters to perform the DFT simulation to get a better understanding and more converged the results. The influence of alloying elements will be studied, and that will be compared to the results of these spectra. Yeah, so yeah, that's it for me. From me. If you have any questions.